to computer organization. And happy Wednesday. So let's see what we're going to talk today. Last class we covered some actually course information or logistics of the class, information about expectations, textbook, and objectives. And today we're going to talk, start introduction to computer organization or computer architecture. And still we are in chapter 1 of the book. And that's mostly about course overview, what we're going to see in this class. Today we're going to talk about definition of computer, what's computer, and of course you know what is computer, but we have other purposes based on that definition. And then we're going to talk about hardware and software, interface between hardware and software that we call that ISA, instruction set architecture, and mostly we are around ISA today, instruction set architecture. So first, let us start with computers. So what is computer? So as you all know, computer is an electrical device that actually accepts some input as a program, as an instructions, and do some processing and make output. You have different type of computers. Some computers called general purpose computers. Like this one, for example, is a general purpose computer. But some computers are actually special purpose computers. Like, for example, you are making a computer for a specific task. Like, for example, you are designing an AI program. You want to have a specific hardware or processor just for processing that specific task. Computers can be servers. You know servers, client servers, you heard about that. When you are working with internet, you're working with servers. Servers are, it might be thousands of computers that collaborating or clustering together to do a task. So they need to be very high efficient and fault tolerance. If something happened, you're not supposed to shut down. Like if you are working with Google or, I don't know, big companies, and if something happened, you don't want to lose all your information. You need to be tolerate the fault to not make failure. And we have minimum systems. We have like mobile computers that are in different devices that are mobile, like real mobile or phone. You have computer inside, but those computers are like embedded computers. We call them embedded because they are inside something else, and they are not general purpose anymore. And robots and so many other, even TVs right now and cars right now, they all have computers, but they are specific purpose computers. So that's the definition of computer. A programmable machine is programmable. You can program it. So it means you can change the program to make different work, different tasks, and accept some input, process it, and according to those instructions, make some outputs. You can store information in the memory. Can be a different type of memory. We have different type of memory, secondary memory, that like a hard drive, or main memory, and produce output. So computers have different forms, as you can see: servers, embedded systems, mobile devices. Computer can have different performance. For some computers, speed is not an issue. Like sometimes you want a computer to be real-time computer. Real-time means a computer that gives response right away or in a certain time, like 10 milliseconds, for example. That type of computer, designing that computer is different. And for some computers need tolerance. They need to work in a different situation. Like, for example, a processor that controlling something critical in your car need to work in any situation. If not working, going to make a problem. Sometimes we call them safety critical computers or safety critical systems because they need to work in any situation without problem. Even we can design some computers that are fault tolerant. Fault tolerance is one subject in computer architecture. How we design a computer that can tolerate actually fault, to not make failure. We have different type of start with error. At first, it's error happening, and then fault. And the fault can be failure or not. Failure means the system gets shut down. It's not working anymore. We're not supposed to let some systems get shut down. The system that controlling the airplane gets shut down is going to be a disaster. So we need to have multiple methods to tolerate that. Those kind of systems called fault tolerant because they are tolerating the fault to not make failure. So we have different performance, different cost, different powers. So for some computers, cost is so important. For example, you are, I don't know, designing a coffee machine. So you need to bring the price as low as possible to compare with other competitors. So you need to use a CPU or processor that is as low as possible, at the same time do your jobs properly. You don't need to use, for example, a GPU for that, and vice versa. Sometimes power is so important. So the system is autonomous and it's supposed to go to forest and stay there for a long time. You need to spend as less as possible, power, electricity to can work, or have some resources to get charged, like using solar or whatever. So that's again different type. You have different performance, different cost, different power, also different manufacturers. Not all computers are Intel, not all are AMD. But many different type of CPUs. If you open your phone, for example, the CPU there is not, for example, Intel is not AMD. Probably ARM, ARM, or sparse, or MIPS. Who knows? Yeah, but we have different type of manufacturers. And actually, I need to let you, if you look at the companies that making, for example, CPUs for general purpose computers, this is not growing that fast. But if you look at the processor that using in embedded systems or mobile, it's growing so fast. So it means you as a computer engineer or electrical and computer engineer, if you want to work in some systems, good to work in those systems that working, I mean, we need them, or people need them more, so to can have more benefits. So working in embedded systems or a CPU regarding to embedded system has more benefit compared to, like, for example, Pentiums or AMD. So, but despite differences between this category of computers, they all have some common organization principles that we're going to talk in this class. The topics that we're going to talk in this class is in general, regardless of type of CPUs, factories, performance, cost. They all have this stuff in common. We're going to talk about those things. But computer architecture. So actually the proper name for your course, instead of computer organization, need to be computer architecture. And actually was. When I was a student, the name of this course was computer architecture. So what is the difference between computer architecture and computer organization is that computer architecture has one extra part. And the extra part is instruction set. It has some extra part, instruction set. So if you want to, let I draw this here. If we draw if we consider instruction set as a level, here we have software, and here we have hardware. This hardware called organization. So the instruction set is an interface between software. This software can be operating system, can be like algorithm that you're writing, compilers, BIOS still is a software part. And instruction set is an assembly language, the language of the machine. That is considered in computer architecture. These two parts together become computer architecture, but computer organization is just hardware. That's the difference between these two. So these two together, computer architecture. But this is computer organization. So we can learn from this picture so many things. For example, if this instruction set is the same, we don't care about the hardware. We don't care who made this hardware, what is the layout, what is the structure of the hardware. As far as the instruction set is the same, you can write a code that works in that machine. So we're going to see that more, and that's why advantage of this interface, we're going to see advantage of this interface today. We call that instruction set architecture later. Right now, we just consider instruction set, but is part of the architecture. So architecture is a combination of organization and instruction set. Okay, so we're going to talk about that more. But why you as a computer engineer or an electrical and computer engineer, you need to know about computer architecture. Sometimes, for example, a car driver maybe doesn't need to know how computer, how a machine works, how automobile works. But why we as a computer engineer need to know what is the actual structure, design, what is the hardware, what is the instruction sets, how is memory works, is it the pipelining, is it superscalar? Why we need to know that? So it depends. First of all, computer engineers are like other engineers. Like if you, for example, you are chemical engineer, you need to know how chemicals react to each other very deeply. For computer engineers also need to, if you don't know exactly how processor works, probably you can't do your task properly. Or if you want to program it, if you don't know how it works, maybe you don't use the advantage of that processor properly. You not get benefits from that. So you need to know that. Like, for example, a bridge engineer need to know exactly how bridge works, how we can design. Or a civil engineer, for example, need to know how design and make house or a building. So it's the same way a computer engineer must understand the system and how it designed and how analyze it. Also, if you want to use high performance, if you want to write the softwares with high performance, you need to actually know exactly how hardware works. If you want to write a code that has a higher performance, you need to use the proper way. You need to use the hardware in the proper way. So understanding the hardware is going to let you to write a better code. This is another reason. The other reason is actually, this is just more explanation about software performance. So efficient programs require knowledge about the structure. Another point, maybe so many people ask you, for example, I want to buy a computer. You as a computer engineer, do you know which CPU I choose, how much RAM, how much, for example, do I need GPU for that? Which graphic card I need to get? This is stuff you as an engineer, as a computer engineer, you need to know. And in this class, we're going to see some of them. For example, somebody asks you, oh, do I need to buy a CPU with this much cache or this much? Which one is better in my application? That is, for example, I don't know, math, for example. So engineers need to know, evaluate, and grade and select hardwares for themselves or for others. So this is something that also you need to know. So in general, like takeaway of this slide is that computer architecture is essential for understanding performance and make decision to choose computers or buy computer, and kind of bridging the gap between hardware and software. So because in computer architecture, you are dealing with instruction set as well. It's kind of between hardware and software. That's a bridge between hardware and software. Okay, that was about computer architecture and difference with computer organization. Let's talk a little bit about performance. What is performance? When a computer working faster, sometimes we call it, okay, it's higher performance. However, it's not always being fast. Sometimes being efficient is also considered performance. Being efficient, like how much electricity used for doing this process, for example. So this is the definition of computer performance, how fast and how efficient a computer system can actually complete a task. So related to task, when you are doing a task, how efficient you do this task. If you do that better, your performance is higher. So we always want to have better performance computer in terms of speed, in terms of power, in terms of security, in terms of reliability, and performance happening in software and hardware. It starts from algorithm. When you as a programmer, for example, designing an algorithm, if you design the algorithm better, so it's going to make better performance. So the algorithm is very important to how much, how good your computer are going to be, how efficient going to be, how fast going to be. After the program, compiler is responsible. So the compiler, if be designed properly, can sometimes make your algorithm working better or faster. So compiler is also important. Compiler change the high-level language, like, for example, Python or C++, to machine language, to assembly language. And then assembly language need to get to actually instructions of the computer in a binary way that called assembler. We're going to see that next class. So anyway, if the compiler works better, it's going to make more performance system. And then processor. If the processor is better, if the memory is more, if I/O is faster, specifically right now I/O is so important for performance. And it all determines execution time, speed, or performance. In general, we have 5 components for computer organization. Okay, we are in computer organization. We are in hardware part now. So in hardware part, we have some input and some output. Input can be, like, for example, camera, can be keyboard, can be mouse, for example. And we have memory. So memory is like a storage that temporarily or permanently store this data that is going in and out. Why we need memory? Because we want to get synchronized. Sometimes input of the input device is, for example, sequential. For example, when you are entering the keys, enter one key at a time. You need to go all in a memory, become a code, become an instruction, become an algorithm, and then go for CPU. So CPU. So CPU is a stand for central processing unit, but right now we just use processor instead of CPU right now. So processor or CPU has 2 parts mostly: control and data paths. Control and data paths together make CPU. data path is also arithmetic and logic unit. It's part of data path. So data path and control together makes processor. This is control. This is processor, and we have a connection between these two. So we have 5 parts: control, data path, memory, input, and output. These 5 components makes a computer organization in general, the hardware part, in a very high level. The processor is actually composed of control and data path. What is the control? Control is like a logic board as well. It's like a sequential logic or combinational logic. Most of the time, combinational logic that has some input and creates some output. So the inputs are based off the instruction. In this computer organization, most of the time, one instruction's executing in a time. Most of the time. Sometimes more, but most of the time, one instruction per time, per clock, for example. It's not always, but yeah. So that instruction has some instruction code. It's like 5 bits or 3 bits. It depends that computer, how many instructions has. So anyway, that instruction code gets output in control and makes some signals. We call them control signals. And these control signals going to around the CPU and make them active and inactive to see how the system works. We're going to see that how we design control. And based off those control signals, this data path, including some shifter, adder, subtractor, and again, depends on the CPU that you are designing, how many instructions you have, and those controls. When the pulse coming, instruction get executed. That's it. It's not difficult in a very high level way if you look at the computer. So the processor is 2 parts: control and data paths. And the control directs operation, as I said, just make this control signals, and data path kind of perform that data processing. So the operation happening in data path mostly. And then memory is between to store the result or actually act as an interface when you are exchanging data with processor and I/O, because they are working different speed. They have different clock. So most of the time, memory is slower than CPU or I/O. I/O are input and outputs are very slower than CPU. So we need a type of interface, and then this memory also has different levels. We call them hierarchy. So we have different types of memory. Some memories are faster. So we're going to talk about hierarchy of memory later. End of this class, we're going to talk about that. Different level of cache, how we can actually design it. We have many different types of cache. Okay, so we're going to talk about that. So that's about memory. But the reason of having memory is synchronization between I/O and processor. And input and output are the devices that are responsible for bringing data in or actually out, sending data out to the printer, to the screen, to any output device that you have. Oh, this is the better picture of that. So as you can see in this picture, we have memory, input and output going to the memory, and this is processor, the control part, controlling everything, making signals for different part of data path, and the data path is actually executing those data and make new data and write them inside the memory. That's actually general structure of a very simple computer. It's working like that. Another responsibility of a computer engineer, I forgot to mention, is that to design a computer, somebody needs to design a CPU or better CPU. So you need to do that as well. And so another responsibility of computer engineer is that. Okay, but as we know, if we can look at a computer in a different way, like you can look at a computer as a, for example, a software designer. You can look at a computer as a system programmer. You can look at computer as a, for example, digital system, or you can look at the computer as a electronic engineer or electrical engineer, that you are dealing with, for example, different things. In that level, you are dealing with, for example, transistors. And you can look at the computer as a engineer that's doing like low-level physical things that happening between atoms. You're designing actually those elements of electronical elements like diodes or whatever that you need, or transistors. So we call these levels abstraction. We want to hide them from others. Like a software engineer doesn't need to know, for example, about what's happening in hardware part. We need to hide that. Other than that, we can't work with that. If a software engineer is supposed to work, for example, in a machine language or designing with gates, for example, combinational circuits or sequential circuits, or go to transistor level, it can't do that. We can't get progress. So we need abstraction. Abstraction means that computers can be understood at many abstraction levels. So the abstraction level showing how you are hiding lower level implementation from higher level implementation. So that's called abstraction. We have different level of abstractions. In this picture, you can see that. You have software part and hardware. Software part is this green part, and hardware part or computer organization is this, I don't know, is it purple? Purple. And this between is the main part that is actually make these applications portable. It's called ISA, or instruction set architecture. So in a software part, you can have an algorithm, you can have your code, you can have your applications. These applications mostly need operating system. In general purpose computers, most of the time, you need operating systems. Like, for example, Windows, Apple, or Linux, whatever operating system. We need some compilers to compile code to assembly language. And this computer, if it's general purpose computer, needs some firmware. This firmware is like a BIOS, how the computer starts. when you are turning on your computer in the first time is start some initialization. That still is software, but the software is in a ROM inside the board that read from that. You can change that. You can set that. For example, you want to boot from this part of hardware. Okay? This is happening in the firmware. So anyway, this is all software. And this software interacting with hardware using ISA, instruction set architecture. So as I said, in the highest level, we have applications and system software. And in middle level, we have actually architecture and machine code that we call that sometimes assembly code. And then in a lower level, we have logic circuits. We have transistors in a lower level, transistors in its circuit design. And the layout is like those hardware, how to organize, how to set these actually transistors together. In logic design, you had, digital logic course. We are dealing with, instructions in that level, gate level. We're designing, for example, subtractor, adder, shifter, register using gates and or XOR and stuff. And in this part, I/O system and instruction set procedures, these procedures is like subsystems. You're designing some subsystems that use many times. So you can consider that as like a procedure of instruction set procedures. And then, yeah, that's it. And each layer hides complexity from the other layers. Complexity from the layers below, actually. So a person that's designing a compiler is just dealing with this, doesn't need to go further or lower. Because if you go lower, it gets more complex and huge. Like in that circuit design, you have like millions of transistors, billions of transistors sometimes. And you don't understand what is working, how it works if you are like a software engineer, or even, for example, as a computer engineer, you don't need to know those stuff to can write a better code. As much as you know instruction set architecture and enough information about how this system works is enough. You don't need to know very detailed low-level parts. Instruction set architecture. That's the interface that we are talking about. So interface between hardware and low-level software. So that's called ISA, instruction set computer, and it has some characteristic. For example, it includes instructions, it includes registers, it includes memory access, how I/O behave. So it's not just instructions, but more information about the hardware. And it's independent of internal processor implementation. And ISA actually enables different processors can run same software. And portability. However, for portability, we need to add another things. So portable software means if you can execute an application an application that is already executed from one computer to another computer. That's called portable. That process, that's an application called portable. But if just ISA is the similar, you still have this problem. You might have ISA similar, but not portable. What else we need to have to make an application portable? We are saying an application is portable when you can transfer execution. Or maybe I ask you in this, actually I made a question. Do you have, let's see, this, I gotta come back. This is actually a question that, yes. Can you access to iClicker? This is actually the same question that I asked you. I want you to answer here. I just want to install that to see sometime we can use this. So which combination is required for point there too? Okay, that's why. Okay, sorry, but oh my God, how I put that away?
You put that in results.
Okay. So which one is C? I think. I didn't tell you. Okay, so C, you mostly answered B, I think. ISA only, but we need operating system. Anyway, operating system, I just wanted to test that, but operating system and ISA called ABI. So ABI is the proper answer, but let's see. Okay, let's go back. Oh, we have time. Yeah, I think we have time. Shoot. Yes, I should put that. Okay, so ABI. Sorry, I should teach that and then do it. I should tell that. Okay, anyway, ABI, application binary interface, is combination of operating system and ISA. So to make a system portable, you need to have same ABI. It means not just ISA, but operating system as well. Operating system and ISA make the system portable. Why? Because operating system needs some, ISA needs some like system calls, interrupt handling, or this kind of stuff that is related to CPU. That's why if you have, for example, a computer that is Intel, for example, Intel 32-bit, if you install, for example, Linux, and if you install Windows, you can transfer executable code or application between these two. They're not going to get run similar. You need to compile it again if it's, for example, C++. So it's not portable. But if the operating system be the same, you can make it portable. So operating system and ISA make this application portable. Okay, so that's instruction set we already had. So instruction set architecture has these parts. Data type like this is for floating points, or for example for integers, for example. That's called data type. We have instruction encoding. We have instruction sets. We have addressing mode. We have if we have interrupt, we need to have that also as part of ISA. Exception handling, we call that exception handling. When interrupt happening, how the system works. We have different type of ISA. For example, we have IA32, is Intel architecture. We have Intel architecture, 64 Intels, and AMD using this ISA. They can switch between 64 or 32. What is 32 and 64 stands for? Any idea? Like probably you have seen one application saying, oh, do you want me to run in 32 or 64 bit? What is that stands for? You know that? Is it? Yes.
Is that the size of a single instruction?
Size of instruction? No. It's not size of instruction, but it's size of something. Size of? Yes?
The amount of addressable memory.
Address?
Addressable memory. Like 32-bit computers can only use 4 gigs of RAM because 49.
Yes. So it's showing what? Size of the address.
Yeah.
Yes. It's size of the address. The address that you can use showing how much memory you can have. If it's 32 bits as an address or 64 bits. If it's 64, it has much more capability to have higher address. So we have a PowerPC, that's another ISA. MIPS, we have a Spark. We have ARM. ARM is another computer. And we have RISC-V that we're going to teach about that. As I mentioned it here. We did that. Example, MIPS is one of the very general RISC computer. We talked about RISC. Do you remember last class? We said RISC. It stands for Reduced Instruction Set Computers. And MIPS is one of those computers. I'm just going to very briefly, from very top view, show this computer. This computer is so small. It just has 32 registers. And some registers are general purpose. Some of them are specific, a special purpose. And we just have 3 type of instructions. Like Intel computers has like 100 type of instruction. This just has 3 type of instruction. R format, register format, and I is for, what was I? Immediate format, and J is for jump. Just 3 type of format. Why we make it so small? Any idea? Why we make processors smaller and everything fixed? To have parallelism, to run multiple code at the same time. We can see how with making a processor small, we can do parallelism. We can do multiple things at the same time, multiple instructions at the same time. We're going to see that later. Okay, so any questions? So next class, we're going to continue about compiler, assembler, and more about instruction set architecture. Okay, have a good day.